Hello everyone, welcome to edupediaword.com. In this video, we will be discussing some questions on Euclid's division lemma. Friends, earlier in the previous video we have studied that for two positive integers a and b, there exist unique integers q and r such that a equals bq plus r, where r lies between 0 and b and r can be 0 also. So friends, on this lemma, let us discuss some questions. The first question says, show that any positive odd integer is of the form six q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. So friends, according to division lemma, we know that this result holds. To show this statement, let a number a or any positive number, any positive integer more precisely, thus it can be expressed in this form, where r will be having these limitations. Now let the value of b to be 6. Thus the equation becomes 6q plus r, where r can be any value between 0 and 6 because b has been assumed to be 6. R can also be equal to 0. Thus the different values of r are r can be 0, it can be 1, it can be 2, 3, 4 and 5, but it cannot be 6. So let us name this equation as 1 and put different values of r in this equation. Thus we will get a as 6q if r is 0, plus 0 will simply mean 6q. A will be 6q plus 1 if r is 1. A will be 6q plus 2 when r is 2. A will be 6q plus 3 when r is 3. Then we will have a as 6q plus 4 and 6q plus 5 for the values of r as 4 and 5. Now friends, a number can be either even or odd. If a number is not even, then it will surely be odd. The even number, as we all know, has 2 in its prime factorization. So This 6q can be modified as 3 into 2q or 2 into the value 3q. Similarly, this value, if we take 2 common, can be modified as 3q plus 1. This value also can be modified as 2 into 3q plus 2. Since these three values are multiples of 2, we can say that these three values are even numbers. Why? Say if we are having a value 16, we can say that it is a multiple of 2 or 8th multiple of 2. So clearly it is an even number. Say we have a value 36. It can also be expressed as a multiple of 2, and we all know that 36 is also an even number. So all the numbers which can be expressed as a multiple of 2 are even number. Now consider 35. It cannot be expressed as the multiple of 5. Sorry friends, in a similar way, you can be asked to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. So to prove such a statement, the first step is as usual to write the Euclid Division Lemma, that is, let for two positive integers a and b, this statement will surely hold according to Euclid's division lemma. Now since we need to prove that square of any positive integer is of the form 3m or 3m plus 1, let the value of b be 3. Thus we will have a as 3q plus r, where r will have the value 0 or 1 or 2. So we will have three situations, that is, a will be 3q, or a will be 3q plus 1, or a will be 3q plus 2, with the assumption that b is 3. Now we need to prove the square of any positive integer. So let us square all the equations on both the sides. Of all the equations, we will get a square is equal to 3q whole square. Here we will get a square equal to 3q plus 1 whole square, and here we will get a square equal to 3q plus 2 whole square. So this term on the right hand side can further be expressed as 3 into 3q square. Now for different values of q, this particular term will be some integer, because q will be integer as per the conditions of Euclid Division Lemma. That is, if q is 1, this value will be 3 into 1 square, that is 3. If q is 2, this value will be 3 into 2 square, that is 12, and so on for the different values of q. So let us assume that 3q square is some value m, which is an integer. Thus we can say that a square is equal to 3m. Now let us square the right hand side of this equation. We will get 9q square plus 1 plus 2ab, where a is 3q and b is 1. So 2 into 3q into 1. On applying the identity that a plus b whole square is equal to a square plus b square plus 2ab. So we will get 9q square plus 6q plus 1. Now friends, from these two terms we can take 3 as common, and we will get 3q square from this term and 2q from this second term, and plus 1 as this term. Thus from the second case we have the value of a square as 3 into this term plus 1. Now friends, for different values of q, this term will be some integer. Say if q is 1, then the value will be 3 into 1 plus 2, which is 5. If q is 2, this value will be 3 into 2 square plus 2 into 2, which will be 3 into 4 plus 4, that is 16. Now since the q is an integer according to the conditions of Euclid Division Lemma, this complete term will also be an integer. So let 3q square plus 2q is a value, say m, which is an integer. So the term reduces to 3m plus 1. Similarly, if we square this term, we will get a square. If we take this value as a and this value as b, then according to this identity, a square, that is 3q whole square, or simply 9q square, plus b square, which is 2 square, which is 4, plus 2 into a into b, which will be 2 into 3q into 2. So we will get 9q square plus 4 plus 12q. Now friends, from this equation, from these two terms, we can take a value 3 common, and we will get 3q square plus 4q, and 4 outside these terms, and this 4 can further be reduced to 3 plus 1. So all in all, this equation will become a square is equal to 3q square plus 4q plus 3 plus 1. Again, this 3 can be accommodated inside these brackets by taking 3 common because this 3 can be expressed as the product 3 into 1. So we will get 3 into 3q square plus 4q plus 1 and plus 1 outside the brackets. Now for different values of q, again this value will be some integer. So let this integer be m. That is, let 3q square plus 4q plus 1 be some value m, which is integer. So we will get a square is equal to 3m plus 1. So in the last two cases we are getting the square of the number represented in the form as 3m plus 1, whereas in the first case the square can be represented in the form 3m. Thus, we can say that square of a number is either of the form 3m or of the form 3m plus 1. So, a square is either 3m or 3m plus 1. Now friends, Euclid Division Lemma was applicable for two positive integers a and b. So a is a positive integer. Thus we can say that square of any positive integer a is either of the form 3m or 3m plus 1 for some integer m, and hence the given question has been proved. Friends, in a similar way you can be asked to prove that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. So for that question, first write the Euclid Division Lemma, take the value of b as 3, then make the cube of all the sides for different equations formed. Then perform the manipulation as we have done here in different parts, and you will get the result or the proof of the statement that cube of any positive integer is of the form 9m or 9m plus 1 or 9m plus 8. Friends, let us discuss the last question on division lemma. The question says a group of 320 students is to be marched behind a band of 28 members. That is, we have a 28 member band and 320 students are to march behind them in a parade such that the two groups are to march in the same number of columns. We need to divide these 28 members as well as the 320 students in such a way that both the groups have same number of columns. Calculate the maximum number of columns in which they can march. We need to calculate the highest value of columns we can arrange these groups into. Clearly, we need some lower factors of these two numbers 28 and 320. And since both the groups are to march in the same number of columns, which means that the factors, the value of those factors should be common to both these numbers, or in simple words, we need highest common factor of 28 and 320. So we need to calculate HCF of 28 and 320, which we have already done in the previous video. So we need to calculate HCF of 28 and 320. We have discussed how to calculate HCF using Euclid's division algorithm in the previous video. So let us take the value of A as 320 and the value of B as 28, because 320 is greater than 28. So the first step was to apply Euclid Division Lemma on both these numbers, and we will get 28 into some value which we can solve by the division process as the first multiple of 28 is the 28 itself and the second multiple is 56. So we will get the value of Q and R as 11 and 12 respectively. Since 12 is not equal to 0, again apply Euclid Division Lemma. On these two values, that is on 28 and 12, let A be 28 and B be 12. So we will get 28 equals 12 into 2, which is 24, plus 4. Again 4 is no doubt less than 12, that is the B here, but 4 is not equal to 0. So again applying Euclid's division lemma on 12 and 4, we will get 12 equals 4 into 3 plus 0. Since R is 0, that is this remainder is 0, the divisor in this case, which was 4, is the HCF of the given numbers. So the HCF is 4. Thus, if we divide both the groups into 4 columns, and correspondingly the members into these columns, we will get the maximum number of columns in which the two groups can march, such that the two groups were to march in the same number of columns. So friends, this was all on the questions on Euclid's division lemma. Thanks friends for watching Edupedia Word videos.